being tidally stripped, which means the clusters are, that for a star cluster, the gravity of the Milky Way is stronger than the gravity that binds the cluster together. Stars from the cluster leave the cluster and exist in tidal tails around the cluster, outside of the cluster. And the boundary where the gravitational field of the galaxy is stronger than the orbit is called the Roche lobe. And the more orbits close to the galactic center, the more tidal streams there will be. Of the 250 globular clusters, the ESA has found 41 stellar streams, which are tidal streams that the Milky Way's gravity has stripped of satellite galaxies and globular clusters, and 46 satellites. The largest of the stellar streams, which you can see in the image on the right, are the Large and Magellanic Clouds, which are dwarf galaxies orbiting the galactic center. We are also using data from the Blanco DCAM Bulge survey. We are currently the only ones using this data, which is really cool. There are 250 million stars in this field, many star clusters, and a lot of dust, which can impede our ability to see stars, which is why we mainly use infrared light to observe them. And the image on the right shows the disk of our galaxy and the bulge of the galaxy in the center, which is where our globular clusters are orbiting that we're studying. And the bulge of our galaxy is slightly peanut-shaped, which makes the orbits of the clusters slightly elongated, which is, sorry, let me go to the next. So we chose 20 poorly studied globular clusters from the BDBS data to study. And we want to determine the distance, the size, the age, the metallicity, and the membership probability of those stars in the clusters to see if they are probably in the cluster or outside of the cluster. And then we'll do follow-up research in the form of spectroscopy on those stars to better determine their properties and their origins, to see if stars have been stripped from the cluster and are in tidal tails, and we want to determine if they were once a part of a cluster. So we use a Hertzsprung-Russell diagram or an HR diagram to determine the age of a star. Stars are plotted on this diagram with their brightness versus their temperature, and the diagram shows the various stages of life of a star to demonstrate where stars are in their stellar evolution. And 95% of stars will be along the main sequence, which is that big line diagonal in the middle that you see. And this is where stars are turning hydrogen to helium in their cores. And because some stars burn up their fuel faster than others, so more massive stars will burn up that fuel much faster, stars will turn off of the main sequence at different points in their stellar evolution, which is where they'll turn away from burning up the hydrogen helium, and a different chemical composition will be present. And knowing the turn-off point of a star allows us to determine the star's age. So the graph on the left shows the path of a younger open cluster, which is another kind of star cluster that has slightly different properties than a globular cluster. And the graph on the right shows the HR diagram of a globular cluster, which is what we are studying. And you can see in the HR diagram on the right, there is a turn-off point where the stars are no longer on the main sequence and are going into the red giant branch, which is also what we were searching for in our clusters. The brightness of the stars is really important as well, because Gaia, what we used, only picks up the brightest stars of a cluster. So knowing their age and knowing where they are is really important to us. So the graph on the left here shows various filters that are placed on the stars, and the filters span across the band of the visible light spectrum. The brightness in these different colored filters corresponds to different metallicities, which is important for the chemical composition of the stars, and different elements will appear different in different wavelengths. And using these different filters allows us to determine those metallicities, and they work best if we use a red or blue filter. And even with these filters, again, we can only see the brightest ones, but we also use this to determine if a star is a field star or a non-cluster star or is a part of a cluster. So another thing that we need to know is if a star is a part of a cluster, how do we identify that it is? And there are some important questions to ask for this, which is, are the stars clustered together and are they moving together? And that's how we know it'll be a cluster, if they're all together and moving together. So the cluster stars should be about the same distance from us, and the number of field stars should increase as we get further away from the center of the cluster. And some clusters may have tidal tails, which is what we are trying to identify. And are the stars moving together? Their proper motions and radial velocities should all be similar to each other. The cluster may move similar to field stars around it, which is another reason why it's really important to separate them. And the tidal tails may move differently because they are not the same shape as the cluster. And this is, again, important to determine because Gaia only picks up the brightest ones, so we need to know which ones are part of the cluster. So we also fit isochrones to the stars in our cluster. Isochrones are paths that stars may follow in their stellar evolution, and there are properties that we can determine if it's on a specific isochrone. And if a cluster of stars falls on a specific isochrone, then we can use that to determine properties like age and chemical composition, and a lot of the things that we need to know about our cluster. So this summer we used Azteca, which is automated stellar cluster analysis, as a method of testing if clusters have tidal tails. So Azteca is a Python-based code program, and it generates stellar models and isochrones based on Gaia and BDBS data that we input into it. And Azteca uses statistics to find the most likely stellar model based on the cluster's data. So these are some examples of the plots that we use. So we use these to determine their tidal radius and the cluster radius, which lets us see how much the difference is and how probable it is that there is a tidal tail, as well as king models, which are simple models that allow us to see the density of globular clusters and tidal radii. And looking at more Azteca plots, this kind of goes through the process of what they do. And the bottom right plot is an example of some of the synthetic isochrones that we fit. And the synthetic isochrones are isochrones that are based on the data that we give it. So it makes it easier to tell what our cluster would look like without all of the field stars contaminating our view. So using this data, Dr. Kunder from St. Martin's University modeled where the red giant branch should be, and she used optical fibers that can observe up to 400 stars at once. And this is really helpful because we have a lot of stars to observe, so it makes the process go quicker and makes observations go faster, which is very nice. And this is an example of spectra that we see, which allows us to measure radial velocity using the calcium triplet, which is an easier way to make spectra and makes observations easier, and it's calibrating calcium absorption to iron abundance. So our initial results from looking at tidal stars, there were 142 stars determined as possible extratidal stars based on spectroscopy and radial velocity. 38 of them showed clearly as being extratidal, and 6 of them were possibly extratidal, but more work will need to be done as this project is ongoing. So initial results, Kevin Covey and Erica Silva from Western Washington University modeled the motion of NGC 6569 to see where escaping stars from this cluster would spread out over the cluster's lifetime of 10 billion years. And Dr. Hughes plotted model escapee stars and learned that the escapees fall where the tidal tails should be, which is really exciting. And that box in the plot, the red box, is the 1 degree area of sky that we searched around the cluster. And our initial conclusions is that we can use the BDBS data and Gaia data to find tidal tails, but because the bulge is very crowded, we do need to keep working on observations. Colors correspond to the metallicity of stars, which within plus or minus 0.5 dex, and detailed modeling requires spectra to confirm radial velocity and track orbits of extratidal stars. And we used Azteca as a way to test a method of finding tidal tails around clusters by inputting our data. And thank you to the Murdock Charitable Trust once again for funding this project.
All right, thank you, everybody. You might have noticed that I've stolen what's going to be a couple minutes of your the 5-minute gap between presentations because I talked for 2 minutes to get us started. So we're on time as planned. Don't panic. What I want you to do now is spend about 45 seconds at your tables and discuss what questions you have. The charge that lies on you now is to make sure somebody from your table is going to ask a question, preferably a student first, from the microphone in the middle in 45 seconds. Go.
Oh, there's my water bottle. I was looking at those, I was like, oh no.
Yes, take a breath.
Yes.
Take a drink of water. You can take your mask off if you want. I think I'm suspicious that it's being recorded in the back.
That's great. My parents wanted a video of it.
I'll take a picture of you in the
Thank
Q&A.
you.
About 20 seconds left. A minute goes by fast when you're talking about fascinating science. Could I get some volunteers to please start making their way towards the microphone in the center to ask some questions of Sarah? This is your obligation as attendance members. This is your job. Yes, please.
I don't know if it's on.
It doesn't seem on.
Doesn't seem like it's on.
Give it a second if you clicked it.
Hello? Oh, there we go.
There it goes.
So I just have a quick question. You briefly mentioned this in your, what are you trying to find? You described how you were classifying stars based on distance and size.
Mm-hmm.
You also mentioned membership. What does that exactly mean?
Right, so when we pull data from Gaia and BDBS, where we pull the data for the stars from, there are stars that are a part of the cluster, and there are field stars which are not a part of a cluster. So we are looking at those stars and trying to determine if they are possibly a member of the cluster, and there is a probability of whether or not they are part of the cluster or not. So it's really important that we know if they are part of the cluster, and if they're not, then we don't want to use them for determining properties of the cluster.
Okay, then. Thank you.
Yeah.
Hello. So I just kind of just recently have been starting to read more about dark matter and such.
Nice.
And I'm kind of curious, as much as I've read about it, it kind of shows that the outer bodies in galaxies follow this rotation curve with a constant velocity. So I'm just curious, if this really relates at all, of just how you took into consideration maybe those dark matter kind of enigma problem issues into your research.
We did not really take that into consideration. It hasn't been a part of it yet. I'm not sure if it will be, but because this project is ongoing, who knows? But we did not take that into consideration, no.
All right, cool, thank you.
Good question, though.
Hi there. So obviously you've had some really fascinating discoveries so far, but the field of astronomy is constantly changing, and across a wide variety of fields we've all heard about, like the James Webb Telescope being, a brand new infrared telescope, and you mentioned that being your preferred method of observation. So how will new methods of observation and stuff like that impact your current project or the future of the project?
It'll probably impact it very well because the James Webb Telescope at least is very good at infrared detection, which is what we use because there's often a lot of stuff in the way of our stars. So that kind of thing is very helpful for observing the stars and gathering new data. So it'll probably be really good.
Thank you.
All right, so I understand how you could get chemical composition from spectra, but I'm not sure how you would get the motion or radial velocities from that. I was a little curious on how that actually worked.
Yeah, so we use parallax and proper motion to determine the motion of clusters and stars. So parallax is using geometry and triangulation to see where they are in the sky at different points, and that helps us determine the motion. And the proper motion parallax is kind of how we view it from Earth almost, and then proper motion is what it's actually doing. So we use that to determine the motion.
Okay, thank you.
Yeah.
And let's thank Sarah one last time.
Well done.
And the next talk is going to begin at 9:25. Lauren Dressler. Thank you, Sarah. If Lauren Dressler is here, I'm happy to get your slides set up. USB drive or something?
I do not have them on
Okay.
USB drive now.
Let's see if we have internet access. This is not my computer, so
Yeah.
let's see. Let's do guest mode. Go ahead and pull it up.
Okay, once we get my phone, I'll be right back. Thank you so much. I've practiced. Dual factor authentication. Oh.
Close the, I thought I closed the Sarah's, but I do not think that I did since it is still presenting. Here we go. Let's close it all the way down.
Oh, good.
And then you can present yours in whatever,
Okay, awesome. Is this a laser projector?
it might be. It looks suspiciously like one. Can you enter, I don't know which way you would like to enter slideshow mode.
Yeah. Oopsie. Slideshow. There we go.
And then what this probably does, I think what I just did, was advance, and then this is probably laser. Yes.
Okay, awesome.
Excellent.
Great, amazing.
All right.
Thank you so much.
And I'm going to be sitting right here, so just be sure to glance at me sometimes because I'll raise this when you have 3 minutes, and
Where
this
you
when you
gonna
have
be
this right here where that computer is.
Awesome. Great.
All right, welcome back, everybody. Grab a seat anywhere. I am delighted to introduce Lauren Dressler. Lauren comes to us from Lewis and Clark and is going to talk about dark matter searches in Legend 1000. Take it away, Lauren.
Is there a way to connect to the screen? Yeah.
It shows up as displaying on our end. One moment. I feel like Moses now from this morning. Present on another screen. Let's try disconnecting and reconnecting, the tried and true strategy. All right. Let's try this. Is it okay if I download it
Yeah.
and open it from PowerPoint instead of opening it from Google Slides?
Yeah.
And we all promise not to hold any formatting changeovers against you. It's in Google Slides.
Pick up the whole window and drag
It's extended display, I see. All right. Thank you so much for that.
Google Slides will not do.
Oops, not share, not share. Yeah, I see. There you go.
Okay, great. Thank you. Hi, everyone. My name is Lauren. I'm a senior from Lewis and Clark College. And this summer, I got the opportunity to work with a group at Duke University doing dark matter sensitivity predictions for an upcoming neutrino experiment called Legend 1000. So to start off with, I just want to give a little dark matter spiel for those of you who have not heard it before. So we think that about 85% of matter in the universe, as we observe it today, is made up of matter that does not interact with light. And this is evidenced by sort of a wealth of astronomical observations, the most notable among these being galactic rotation curves, where we would expect sort of stars on the outside of galaxies to move a lot slower than we actually observe. And the simplest explanation for this would just be to say that there has to be a lot more mass towards the outsides of these galaxies than we actually see. A second piece of very important evidence for dark matter comes from the cosmic microwave background. And the cosmic microwave background is relic radiation from the Big Bang, right? So this is sort of our earliest snapshot of what the universe looked like, just a couple 100,000 years after the Big Bang. And looking at the temperature fluctuations in the cosmic microwave background, we're able to sort of see what the structure of the universe was like at this time. So we can see how mass and energy were distributed during this time period. And when we compare that to the large-scale structure of the universe today, so galaxies and galaxy clusters that we see today, what we see is that we would need a lot more mass than we actually observe to account for the formation of those large-scale structures on the timescale of the universe. So yeah, based on these observations and several more, we think that about 25% of the total mass energy of the universe needs to be dark matter. And I just want to go through one more sort of landmark piece of evidence for dark matter, which is the bullet cluster. So this was a series of images taken in 2006. And the bullet cluster is actually two galaxy clusters which collided and passed through each other. And so what you're seeing in this first image, these two blue shaded regions here, these are where we would expect the mass in these galaxy clusters to be based on gravitational lensing, which is where light bends around massive objects. However, the Chandra X-ray telescope took a picture of the same piece of night sky, seeing X-rays in the regions where we would see hot gas in these galaxies. And hot gas makes up a large proportion of the matter in these galaxies. So if there were no dark matter, we would really expect these two images, when they're overlaid, to see the X-rays and the location of gravitational lensing in the same place. But when we overlay the two images, what we see is this sort of mismatch where you get the X-rays from the hot gas towards the center of this collision, and then more gravitational lensing on the outside. And what we think this means is that dark matter does not strongly interact with itself. So where the normal matter was able to experience sort of the drag force of a collision as these two clusters passed through each other, the dark matter just continued moving and did not interact with itself. So yeah, this is sort of the smoking gun as far as evidence for dark matter goes. Yeah, and so based on all of this, we're sort of able to loosely assume what some of the properties of dark matter would be. So we know that it won't interact via the electromagnetic or via the strong force. We know that it needs to be a stable and long-lived particle because we still see it today. It definitely interacts via gravity. And the question is whether or not a dark matter particle would interact via the weak force. For the sake of this project, we assume a model of dark matter where it will interact via the weak force because that is what would make direct detection of a dark matter particle possible. Yeah, so we know this stuff is out there, but the question is, what are we looking for, right? And the issue is that this search spans a huge mass range. So we could be looking for a particle that's lighter than an electron, but we could also be looking for something that's 10 solar masses, right? So huge. This really spans 80 orders of magnitude. And I just want to highlight one specific model of dark matter that has been particularly popular and will be relevant to my work later, which is the weakly interacting massive particle in the GeV mass range. This model is very well motivated by theory. However, several decades of trying to detect these particles have come up entirely unsuccessful. And so now we're sort of trying to tweak that model a little bit and see if we can find sort of slightly different candidates that would potentially be viable dark matter candidates. So today the criteria to be a dark matter candidate that we want to look for is that you don't horribly violate any of the known laws of physics, that you don't conflict with any of our current observations of dark matter, and that you have not yet been ruled out. So how are we going to start ruling these things out? Well, we build a parameter space where we represent different dark matter candidates with respect to their mass. This is what we're seeing on the horizontal axis here. And with respect to their cross-section, so with respect to their probability of interacting with normal matter. And then we're able to say that certain experiments will be sensitive to certain types of candidates. So these different lines here, sort of any region above this would be the types of dark matter candidates that these experiments would be sensitive to. Yeah. So as far as running detection experiments goes, there are three main methods for dark matter detection. The first of which being indirect detection, where you assume that dark matter has, similar to normal matter, an antimatter particle, and that when these two particles meet, they would produce some standard model particles, which we would be able to detect. The second method to detect dark matter would be using colliders. So this is pretty self-explanatory. You just get a huge accelerator and you collide particles together and hope that you get a dark matter particle out. And the last method being direct detection. Now, usually with direct detection, we would be looking for weakly interacting massive particles, and we would be looking for a process known as elastic scattering. And what happens in elastic scattering is you have an incoming dark matter particle that comes in and hits a nucleus in your detector. And the kinetic energy of that dark matter particle gets transferred to the nucleus that it hits, and it gives that nucleus a little recoil kick. And this leaves a footprint in our detector. So we would see ionization, so we would see charge deposited somewhere in the detector. We might see scintillation, which would be light, or we could see heat. and make sensitivity predictions for which types of dark matter candidates Legend will be sensitive to. Yeah, and I'd just like to thank the Barbeau group at Duke University for allowing me to conduct this research with them this summer, and I'd also like to thank all of my professors at Lewis and Clark for their ongoing support. Yeah, thank you very much.
Thank you so much. Wonderful talk. Again, about a minute in your tables, discuss your thoughts on the questions you have. It's a big relief. You did great. You did great.
No, I was a little bit nervous, but you know what? I think it went okay.
Whenever you have a question in mind, you can go ahead and line up at the microphone. We have time for maybe 2 or 3 questions. I know there's at least one more question in the audience. Be brave, somebody. Yes, excellent. All right, I'm going to hand it over to take questions.
I had a question about your graph of possible dark matter particle candidates,
Yeah.
the one that had cross-section plotted against mass.
Yeah.
Wouldn't the cross-section of the dark matter particle depend on what it's interacting with?
Would the cross-section of the dark matter particle depend on what it's interacting with? That is a great question. I think generally we're looking at, these interactions for weakly interacting massive particles, we're looking specifically at weak interactions, right? So we would be looking at interactions with a nucleus, so with a certain type of quark, either a down or an up quark in the nucleus. Yeah, but there are definitely different probabilities associated with different elements that could be factored in. I think that in this plot, it is probably with respect to a single element for all of these different candidates. But yeah, there are a lot of different parameter spaces which can be built.
Thank you.
Totally.
Hi. So I'm not super familiar with a lot of the physics. I've just read a little bit, but I don't know if color charge is that. I think that's related to the strong force.
Mm-hmm.
I'm wondering if because dark matter doesn't have color charge, they wouldn't experience a strong force.
Yeah, it's true. So we think that dark matter does not interact strongly, so it would have no color charge. Yeah.
Okay.
Yeah, totally.
There was a slide where you had a scale of masses,
Yeah.
and you went from, right. I was wondering how you differentiated between KeV for units of mass versus units of energy.
Oh, yeah, totally. So because we have this mass energy equivalence, right, in physics, E equals mc squared, it becomes easier, to measure the masses of very light particles with respect to their energies, right? So we measure in electron volts generally in particle physics. Yeah,
All right, thank you.
totally.
Why germanium? Is it just particularly good at weak interactions?
Yes, germanium is awesome for weak interactions, and it's awesome for all types of neutrino experiments.
Okay. Thank
Yes.
My table had a bit more of a general question. We were
Yeah.
talking about, our understanding was that this is kind of like background work for potential actual experiments with Legend 1000. We wanted to see if that was correct and what the plans are.
What plans are for?
What kind of physical experiments would you hope to do once it's a possibility?
Yeah, so Legend is, I think, going to be built in the next decade. And once it starts collecting data, we would really just be looking in that data, sort of searching for these signals that we're interested in. So it's looking for a different type of particle decay. But if we were able to look at the data which Legend is collecting and see sort of a different signal that maybe they may have dismissed, that might be important to us, then that would sort of be something that we would hope to do. Yeah.
That's really cool. Thank you.
Yeah, totally.
Let's thank Lauren one more time. The next talk will begin at 9:50, and if Nick Wild is here and could step up to the front. Okay, excellent.
Is there somewhere we could we're so analog.
Oh, we can use that.
Okay, I have my own.
Yes.
Oh, perfect.
Let me orient you. That's why I asked you to come up. Hello. How are you
Hi,
feeling?
I am nervous, but I'm excited, and this is really cool work, so.
Excellent. You're co-presenting, so I'll be sure to introduce both of you.
Thank you.
Logan Banks. Is that
Logan
what you're-
Banks, yeah.
Excellent.
We'll introduce ourselves at the beginning as well, so.
The
I can just use it. That way we don't.
let me bring up this presentation. Hopefully, is the one that you're expecting.
Yeah. Could we skip to the first slide? So sorry.
No, you're good. Starting at the beginning is a reasonable approach.
And then we're also pulling up a model within it, so on one of the slides.
Do you want to check?
I tested it earlier.
We tested it earlier, it should be fine. We just
give
want
it a
to,
quick
we'll
warning.
prepare everybody for that.
Okay.
It's a little stuttery with the Wi-Fi. So.
I see. Okay.
Okay.
So the way this works is this button will go to the next slide. This button will go back a slide. This button up here is the laser, and then I think this would close it. I haven't touched it yet.
Thank you.
So you're welcome to use that. You're welcome at any point to grab water. That's why it's here.
Excellent.
Okay.
I am going to be sitting right here by this empty computer, and when you have 3 minutes left, I will hold up this 3-minute sign. So just be sure to check in with me so that you notice that sign. Perfect.
We'll look studious. Come on, come lean against the podium. We'll pose. Ooh. Super. Do I have time to pee? What time is it?
Here, you take the.
Okay, no.
You take the thing.
Here, I can. Are you sure?
Well, yeah, because you can advance the slides with that one.
Okay.
So it was right to advance.
Ready?
We got 1 more minute.
Okay.
This is the worst the nerds get. Once you start talking, it gets easier.
Oh yeah.
Just gotta move it up.
We'll let you take over the microphone.
And we won't touch any buttons right now.
I don't want to start you early because people will probably come in for your talk and then they'll be like, oh no, I'm late. They've already started.
Oh yeah, it's fine. Don't worry. You can. It's gonna be so good. It's already on the resume, so it's already there.
Don't worry, don't worry. You're just you've prepared for this moment. You're ready to go.
For this one.
You're ready to go. You got this.
Okay. I like mine. That's
All right, welcome everybody. Find a seat if you're joining us. I am delighted to introduce Nick Wild and Lauren Banks from Willamette University. They're going to present to us about Marble That Matters, an unmanned aerial vehicle-based research of classical period Greek quarries. Thank you very much.
Hello, everyone. I'm Nick Wild.
And I'm Logan Banks.
We are archaeology students from Willamette University.
Over the summer, we worked on a project funded by the NSF in Greece under the direction of Dr. Scott Pike for the Willamette University Archaeology Department.
Welcome to Marble That Matters, unmanned aerial-based research of ancient Greek quarries.
In studying these quarries, we sought to identify the chronological extent and physical expanse of the southeastern quarry complex on Mount Pentelicon.
So to begin, what is the historical relevance and context of these quarries? So these quarries were the primary source of marble for the Periclean building program starting in 447 BCE, including the Parthenon. Literary sources indicate that the quarries were used in the classical period, and physical evidence indicates that they were used as early as the Greek Archaic period, over a century prior. The marble was also a primary economic resource of the city of Athens and its ancient trade networks, being one of its local resource mines, along with silver.
This map shows the southeastern quarry complex right there on Mount Pentelicon, which is right there. And there's Athens, positioned in Attica, Greece, which is, of course, a country.
Can we go
so
on back?
sorry.
No worries.
Wow, it skipped forward a lot.
I want one more forward.
Okay, there
Thank you.
we go.
Okay, perfect. So our project was broken up into two broad categories, the physical extent and the chronological extent. I was primarily focused on examining the physical extent of these quarries, focused on how large the quarry complex itself was, how large the individual quarries inside of the quarry complex were, and how much material was removed from those quarries during the ancient usage periods.
For the chronological aspect of the research, I investigated two main questions. First, can vegetation patterns along quarry walls be used to date one section of a quarry when compared to another, so establishing a chronological portion of the quarry? And then the second question is, can multispectral sensor technology, equipped UAV drones, successfully model complex terrains?
So to establish my goals, it was first necessary to assess the quantity of material removed from these quarries. To do this, we used 3D photogrammetry models generated from aerial vehicles taking photographs of the ground for data collection, from which we could analyze the volume of material removed. In order to analyze the volume of material removed, however, we needed to determine which quarries were in fact ancient and which were modern, which was complicated by modern quarrying in those areas. And lastly, we needed to, of course, contextualize these quarries and figure out their historical relevance, which was done through primary and secondary source review and prior scholarly research. So what can the physical extent actually inform us about? Primarily, it gives us a clue as to the industrial usage patterns of these quarries in ancient Greece, how they would have quarried them, what they would have quarried them with, and the industrial importance of them, as well as the exported and imported material in the city, and which buildings in the city were constructed from that marble. A quick background of photogrammetry is, of course, necessary to understand the primary methodology of this project. Photogrammetry is a process of taking two-dimensional images and then matching the shared pixels between them in 3D space, from which a point cloud is generated, and then triangle mesh is created between them to create a 3D model. Here you can see a sort of stylized version of that, the intersecting points, of course, being the vertices generated from those shared pixels, and the lines being the interpolated information.
As for the chronological research, I had one base principle that I really kind of investigated. It was that vegetation biomass accumulation over time indicates age. In areas with a higher chlorophyll content due to density, maturity of vegetation, or higher total cover of plants, it can be assumed that average age is older than one where the vegetation is less rich. My goal was to model a quarry with multispectral data that can identify chlorophyll content, bare dirt, and stages of development through the vegetation type, which can later be used to interpret patterns of growth along the quarry wall and base, and may be able to indicate the age of sections of the quarry relative to other portions. My secondary goal, of course, was modeling a complex terrain. Current multispectral work is often done on flat or non-complex terrains, mostly used in agriculture. This project models a quarry which has complex areas of shadows and dramatic slopes, functioning as a proof of concept for multispectral equipped UAV in non-standard landscapes. So, what is multispectral? And also, what was my method? For the most part, my data that I collected for the chronological portion consisted of multispectral band photo sets. I used the Red Edge dual camera sensor, which is a 10-band multispectral sensor that captures light frequencies from 400 to 900 nanometers. The system consists of the MicaSense Red Edge X and the MicaSense Red Edge X Blue to span a larger capturable reflectance. The visible light spectrum extends from 400 to 700 nanometers, as you may know, meaning that the Red Edge sensor is able to collect frequencies in the near infrared. And then I have this diagram here, which displays the 10 different bands, those, that the Red Edge is able to capture according to their position on both the visible and the non-visible spectrums. As we can see, the Red Edge fills in the gaps where the Landsat 8 and the Sentinel 2A multispectral systems do not collect data. Vegetation reflects light through photosynthetic processes that cannot be detected in normal light, but can be detected using near-infrared and non-visible spectrums. For each photo taken, 10 true images, so sorry, that's a little bit of a tongue twister, are collected, which can be combined into a multispectral map. The different map bands can be used to identify specific features, like leaf area index or drought index. For this study, however, I utilized the Normalized Diversity Vegetation Index. The NDVI created a map that was able to determine patterns of green vegetation and chlorophyll content, which could create patterns that I could use to analyze chronological age.
So, of course, with any project, there's a number of challenges that accompany it, and we were no different. We had issues with battery management, heat and weather, and of course, data processing issues. So the heat in Athens is quite extreme, especially during the summer, which shortens the life of the lithium battery cells we were using, limiting data capturing potential. Due to this data capturing loss, we also had issues with data processing. During the days in which we were able to work for extended periods, we collected too much data, which is a little bit of a funny problem to have, but it resulted in quite a few issues later on in the project when we were working with the models themselves, in which we were spending more time discriminating between our own data rather than working with the models and interpreting them.
And finally, to results. So this generated, this generated map shows the NDVI map model separated by a Jenks statistical differentiation, and don't worry, I will explain that. Purple values represent barren rock with chlorophyll content increasing as the percentages increase. So starting from purple, the order is barren rock to greens, lichens/mosses, grasses, shrubs, and finally trees. This identifies patterns of growth along with stages of development in the vegetation. In separating the discrete values of data, I employed the Jenks statistical operation. This seeks to minimize variances within the same classes and increase the variance between different classes. This more accurately displays the patterns within the model than other classifications like equal area or equal percentage. And then, let me explain these tables a little bit. So the first table on the left displays the chlorophyll content values ranges for each group. The second table displays the area in hectares of each group, along with the total cover percent, so that's why it totals 100. As we can see, the area that we surveyed has a really low percentage of barren rock, but mostly contains shrubs and medium-sized woody plants, which would be like right here, which is pretty interesting. And then finally, this map displays the quarry proper. So this right here is kind of where we surveyed. It's the top of the quarry. This is the bottom. As we can see, the purple barren rock is concentrated near the base of the quarry. It's kind of hard to read on here. And then this is like a road. And then we also know there's some ancient quarry roads over here that are also purple because they are barren rock.
All right, hello everyone. So this slide may present some issues. We're trying to get the 3D model to appear. Just a sec. I can get. All right, so in theory,
oh no,
it's okay. So in theory, this should pop up with the model.
It is.
Oh.
Oh, nice.
All right. Give it a sec here. So the 3D model we generated was generated with models captured from a DJI 200 Matrice as well as a DJI Mavic 3. So we have some bonus slides if this doesn't load at the end that show like still shots of this, but basically the model is a 3D model of the quarry itself showing vegetation layers and the elevation. Oh, here we go. Okay, so this is a little bit lower quality than it ought to be, but that's all right. You can still get sort of an idea here. So from this model, we were able to calculate that around 22,500 cubic meters of material was removed during the ancient period. From the ancient quarry walls. So on the side here, you're seeing some very deep cuts. Not all of those cuts are the ancient material. The ancient material would have been cut higher up, and then modern quarrying would have gone down. Maybe if we have extra time, I can show the slides at the end that show that more clearly. Unfortunately, the model doesn't appear. Oh, there you go. It's just loaded. So as you can see, there's a color differentiation towards the top of the model, which I can hopefully zoom in a little bit on here. Maybe not. Okay. So so if I was able to zoom in on that right now, you would see that there is a color differentiation where the older material is a darker color due to lichen growth and age. All right, and then finally our interpretation.
Oh yes, of course. So sorry. So we have obviously two different projects, so I'm going to go first. The chronological map that I showed actually indicates no pattern for chronological dating based on known exploitation practices, which are kind of broadly defined based on historical data that we have and also proxy data, so we assume that they started closer to the city, which is a pretty good assumption. Nor is the vegetation consistent enough to derive a pattern that is chronologically relevant or assumable. Basically, it's kind of scattered everywhere. However, UAV-employed multispectral analysis hasn't really been conducted on surfaces similar to this quarry. In its function as a proof of concept for multispectral analysis on unequal elevations in differentiating terrain, it was successful.
In terms of physical interpretation, on top of being able to determine the volume of material removed, we were also interested in analyzing if the quarry size related to period of use, so if older quarries were smaller and later quarries were larger, which we suspect is true, and if there were consistent quarrying patterns where we could see what areas they were prioritizing. Unfortunately, ongoing research will be needed to determine that. This project is going for another few years, so this interpretation work is still very much in progress. And then in terms of other implications of the project, the archaeometric implications, use of UAVs in archaeology is a developing field. It's very new, and we're hoping that this study and project as it goes on can help to build a series of best practices for analyzing ancient quarries utilizing UAV technology and photogrammetry.
Marble and other stones used in antiquity, as well as the geoarchaeologists who study them, consider quarries, mines, and excavation sites as a crucial part of the process by which humans interacted with ancient material. Learning more about these places, like the Pentelic quarries, offers us valuable information that cannot be learned from studying only artifacts. This research shows that open area sites, like quarries, can be modeled and studied for removal rates, size, and complexity.
And finally, as previously mentioned, this is part of a 3-year ongoing research project funded by the NSF, so future work will be done under the direction of Dr. Scott Pike at Willamette University. We would like, here's our acknowledgements. We'd like to thank the NSF, of course, for funding us, the Murdock Conference for having us, and Dr. Scott Pike for taking us to Greece. Thank you so much.
Thank you so much for that wonderful presentation. Now I am here to direct you all back into your groups at your tables. Please take about a minute and talk through your thoughts and any questions you have.
I'm ready to hit you with a question if you are.
About 15 seconds left to collect any thoughts. If you'd like to stand up at the mic and move yourself that way to begin asking some questions. We'll take questions in about 10 seconds.
I'm so excited for questions. I feel like I know my content, but I don't know.
It's also probably fine to figure out.
I'm like a baby genius with food sarcasm. That was a weird joke.
All right. And now for questions.
Hi. I was curious, was there any particular reason there wasn't like a LiDAR base?
Yes. We don't have LiDAR.
Okay.
That's the issue. We're trying to get funding currently for it. Obviously, funding is one of those things that is kind of hard to come by, especially for a technology as expensive as LiDAR. There are so many implications for this research using LiDAR, and in future years, we do hope to have it.
Cool.
And kind of expand on the library of data that we already have.
Awesome, yeah. And I was curious, like, what kind of, if I was another researcher and I wanted to do something similar, like, what kind of software suites were you guys using to analyze the photo data?
Yeah, so we were using a few different softwares. Primarily, we're using the Pix4D software. This was done because of its integration into GIS and its compatibility with geospatial science methods. In addition to that, we were, of course, using GIS technology. So
cool.
Primarily,
and that was just like pretty like mundane. Like you could run that on a regular computer. Nothing. You don't need a computer.
You'd need a fairly powerful computer to process the number of images that were required, but it can be done on a relatively standard computer. Yeah.
Cool. Thank you.
Hi, great job, by the way. We were curious how you were able to calculate the volume of material extracted from that 3D model that you shared.
Yeah, so Pix4D, as part of its software suite, is able to take that point cloud and from that interpolate the structure of the quarry itself. And then it has tools built in that are able to take those 3D points in space and calculate the volume removed from it. The model we were showing isn't nearly as accurate as the one that we were actually working with. So we are relatively confident in its accuracy. In future years, we hope that the number will become more specific and get narrowed down further, especially because this year we were working with fairly conservative data as we didn't want to capture modern quarrying.
Thank you.
I had a question about, so you used vegetation for dating.
I sure did.
I was wondering if you thought, or if anybody else has done work using like lichenometry or
Oh my
other
God, I love
exposure methods.
lichenometry.
Yeah.
Thank you for asking about it. Okay, so I'm also an environmental scientist, so being here is scary. But lichenometry was actually the base principle I talked about. Let's see if I can go back all the way. Yeah, so the vegetation biomass accumulation over time is actually a principle of lichenometry that you kind of study in beginning environmental science classes. I'm just kind of extrapolating it to probably the broadest extent you could. But it is actually a pretty easy principle to follow. So that is like a really good basis of lichenometry is that. So I also talked about briefly here, that blue value is actually greens, lichens, and mosses because they're going to be smaller than grasses and project some photosynthetic light waves, but not as much. So you can actually see them on here, and we can kind of guess. Can you see my? No. You can kind of assume that if this is the base, these are the walls, and this is also kind of like the base and the walls. So we actually see a lot of lichens along the walls here. So yes, I did use lichenometry. So
Cool. Were you able to ground truth as well to go with?
Yeah,
the remote
we definitely
data?
did a lot of scouting, about 2 or 3 days worth, where we just kind of walked around, took some photos. We have some at the end. Is it okay if I show them?
Of course, yeah. We heavily utilized ground control points.
Yeah.
So a lot of the project was actually in the field placing those points and figuring out where they could work best.
And this is a very large quarry, too, so it took
It's-
quite a lot of work to scatter around.
With those ground control points, we used a GNSS system to use satellite information to get their exact location.
Cool. Great. Thank you.
Super. Thank you.
I had another question about field work from your work. You analyzed analyzed the multispectral data to understand understand the quarry. I was wondering if the team has taken in-field measurements such as like a leaf area, or they plan to with this work.
Mm-hmm. Not currently. This is kind of just drone-based for now. However, obviously that would be very interesting future research. We just don't currently have plans for that because we are trying to focus on the extent that we can use multispectral data to map these things.
Mm-hmm.
And also, vegetation in this quarry is kind of hard to find because a lot of it presides on the quarry wall itself.
Mm-hmm.
And they are very tall quarries. So you'd have to be an excellent mountain climber to do that.
So it would be impractical.
Yeah, a little bit. Just a little bit. But I mean, you could definitely do like the base and see if it matches up pretty well.
Okay,
So, yeah.
thank you.
Thank you
Of course, thank you.
Thank you. Let's thank Logan and Nick again. All right, we have a short intermission now. The next presentation is Nicole Henry at 10:35. If Nicole is here now, I can give you a quick heads up before you head out for the break. See you all here again at 10:35. Hello. Just want to double check that everything shows up. Do we already have your presentation?
I believe so.
Okay.
I went through great lengths to figure it out. I think I ended up having to email it to someone.
Oh, interesting.
I like your name, by the way.
Oh, thank you. Yeah, it's done well for me so far. I hope it does well for you. Yeah, we have one. Let's see, that's not you. This is PS4, your PS4. Let's see if it's in here. Aha, Nicole Henry. I found you. I found all of them. They should have told me about that folder before.
Do you mind if I look through it?
Yes, that's why I wanted you to come up during the break.
Oh, yes. because there was some issues. I do have like a animation on this slide.
Yeah, so if you click the animations, it'll show if it is seeing any. And you're also welcome to go into presenter mode.
This one?
Yeah, and protected view. There we go.
Beautiful. Oh. Oh.
That's okay.
A little sneak peek, I guess. Oh, that's amazing, man. I was so worried.
Yeah.
Because I tried to submit it in the Dropbox, and it was unreadable. So they couldn't open it for the longest time.
But we got it.
Yeah. Wonderful.
Delightful. So the way that this works is this button here, when you're in presenter mode, I'll go back to the joy of being right after an intermission is also that your title slide gets to stay the longest, so I'll put it up now. And the way that this works is if you press this forward button, it'll advance your slide. You can go back with the backwards button. And this top little, exactly, so if you need to point to anything, you can use that. That is just right here. I will see, we had a couple water bottles. I'll see if we have some extra. Ah, yes. I'll find some replacements, and if you need water, it'll be right there.
Okay, wonderful.
I sit right at this computer, and I have a little sign, not this sign, different sign. One side says 3 minutes, one side says 1 minute, so I'll try to give you a little hint about how you're doing this time.
Awesome.
Just be sure to like check in that corner so that I'm not like trying to get your attention.
Awesome.
Beautiful, excellent. All right, now enjoy your break, and I'll see you in like 45 minutes.
Yeah, 10:35, right?
10:35, so 22 minutes.
Awesome.
Great.
Thank you so much.
Of course.
Except the people who are doing it, right? So you need more people to judge. So yeah, that's really.
I will, when I hand it over to you, I'll sync here so you'll also see live the time, but this is the sign, the 3-minute sign and 1-minute sign.
Awesome.
All right, we're going to start in a minute, and so if you need to find your way to your seat, I invite you to do so now. Everybody was ready immediately. You've got a whole minute. It's always the longest minute when you're like, it's almost there.
We got this, Nicole.
And there's water there if you need it. Thank you so much. All right, it is my honor to present Nicole Henry, who comes to us from Pacific University, who's going to talk about assessing the rate of seasonal phthalate inhalation through air sampling in forest growth. Take it away.
Thank you so much. Thank you all for joining me this morning. I'm super duper excited to be here. Thank you for introducing me as well. So my name is Nicole. I'm from Pacific University. I'm a chemistry major, and this morning I have the pleasure of sharing with you my research project, assessing the rate of seasonal phthalate inhalation through air sampling in Forest Grove, Oregon. Now, before we begin, I would like to invite you all to join me to take a nice, deep breath. Ready? Has anyone ever thought about what we just breathed in? No? Just me? Okay. So phthalates are a large class of semi-volatile compounds that are detected in every environmental media, from cosmetics, kids' toys, to food packaging and other plastic products. Some derivatives of phthalates are endocrine-disrupting compounds. The image of the phthalate on the bottom here, diethylxyl phthalate, or DEHP, is arguably the most commonly used phthalate. Its job is a plasticizer, which means it's added to plastics to enhance the qualities of plastic, making it more durable, flexible, and last longer. Now, the reason that we care so much about phthalates is because some derivatives of phthalates are endocrine-disrupting compounds. This means that when inhaled, ingested, or absorbed, they have the ability to interfere with and/or block normal hormone function in the body. This can lead to adverse effects such as decreased fertility, lowered sperm count, obesity in children, and early onset puberty in children. So worldwide, there really haven't been that many studies done in phthalate detection in outdoor air. The most recent ones have been done in Asia, with some in Europe, and a few in North America. Based on these figures I have here, you can kind of tell that there haven't been any in the United States, not since the early 2000s. So in Asia, we have concentrations of phthalates in the atmosphere ranging up to almost 1,000 nanograms per cubic meter of air. And in Europe and North America, they're ranging up to about 150 nanograms per cubic meter of air. And as I mentioned, there really are no studies done in phthalate detection in outdoor air in the United States, so we don't really have an idea of what these concentrations look like here. And so that's where my project begins. I would like to fill these gaps in the United States by beginning to sample for phthalates in outdoor air in Forest Grove, Oregon. And so that is a approximate location of Forest Grove in Oregon, if you've never heard of it before. The picture on the right depicts the 2 air sampling locations that we have in Forest Grove. So that's the campus where I go to school, Pacific University. The other part of my project consists of assessing risk through phthalate inhalation, and so my goal is to help measure exposure rates by using the phthalates detected in the air in Forest Grove. And once I get these detection rates, or these concentrations in the air, I am able to calculate inhalation rates for a specific person over the course of a day, for example, and then we can use that information to assess risk. So my sampling begins at these lovely trailers that we have. Each trailer is equipped with several air sampling instruments, of which I will be using 2. One is called a BAM, and that one samples for total hourly particulate matter concentrations, or PM10 concentrations. PM10 basically means particulate matter that is 10 microns or less in diameter. So the BAM samples for total PM10 concentrations. And the other instrument I will be using is called an EFRM, and that one I manually insert a filter in, it's about this big, and I put it into the instrument, let it sample for 24 hours at a specified flow rate. And once it's done, it looks like the picture on the right here, loaded with particulates. And I bring that back to lab to be extracted. So the first step in my extraction is a sonication, which dislodges the particulates from the filter, followed by an extraction and cleanup step using solid phase extraction, which isolates the phthalates from the rest of the particulate matter. And then lastly, instrumental analysis using a GCMS, or a gas chromatography coupled with mass spectrometry. Now, I have to remind you that phthalates are ubiquitous contaminants in the environment. And because of that, we do have to ensure a lot of quality control in our lab. And this begins with method detection limits and instrument detection limits. And I know it's kind of a heavy figure. You don't have to worry so much about it. All these numbers mean is that I cannot report data above these or below these values. These are the absolute minimum concentrations that we can detect through both our method and the instrument itself. Now, the other part of quality control consists of positive controls, calibration checks, and negative controls. Positive controls are samples that I deliberately spike with a known concentration, carry it through my method, and quantify the concentration at the end and see how much was recovered. So we have ranges from 74 to 122%. Calibration checks are known concentrations that we run directly on the instrument and tells us whether or not the instrument is quantifying everything properly. And it is, as the recovery rates are 95 to 106%. Negative controls are probably the most important, as phthalates are ubiquitous contaminants. They do show up in the lab even when we don't want them to, and one of the ways we combat that is by negative controls. So these negative controls pick up any sort of contamination in the lab, and then we are able to method blank subtract all of our data so that we don't report any contamination in our samples. Once all of our data is finally method blank subtracted, we're able to make a graph that looks like this. So these are an overarching graph of our results. So this is the sum of 14 phthalates detected in 10 different sampling dates over the summer. So pretty cool. Now, as I mentioned earlier, I use 2 air sampling instruments. One is called a BAM, and the other is called an EFRM. The BAM samples total PM10 concentrations in the atmosphere, and the EFRM is what I use to isolate the phthalates from the rest of the particulate matter matrix. And so I wanted to see if there was a correlation between the total atmospheric concentrations and the phthalates detected in the total atmospheric concentrations. And so far, I have not found a correlation. But this isn't entirely unheard of, as in places like Lebanon and Beijing have also reported no correlation and weak correlations, respectively. But just because I'm not the only one who has reported no correlation doesn't mean that there aren't other places that do report correlations. So Beijing, for example, they have positive correlations between total PM10 concentration and the phthalate detection. And so the main point of this is that we don't quite understand the relationship between total PM10 concentration and the phthalates detected within the atmosphere. So as I continue my study, I will continue monitoring this relationship to see if one develops or if it continues to stay this way. So a deeper dive into my results. If you remember earlier, that phthalate I was talking about, diethylhexyl phthalate, it's the most commonly used phthalate as a plasticizer. And so, unsurprisingly, that's the one we detected at the highest concentrations throughout all sampling dates, followed by DIBP, DBP, and DBEP. These are also used in many other ways, not only just as plasticizers, but sometimes they're added to PVC pipes, ink, adhesives, makeup, nail polish, perfume, all kinds of other things. So they are ubiquitous contaminants. They're found in every environmental media. So if you haven't noticed already, if you remember from earlier, I did mention that the concentrations around the world are upwards of about 150 nanograms per cubic meter. And my concentrations are up to 13.7. So the concentrations I've detected are far lower than those detected across the world. One of these reasons is potentially the fact that I am sampling in a rural area as opposed to an urban area like China, for example. But even though my concentrations are far lower than those detected around the world, I'm still detecting the exact same identity of phthalates. For example, DEHP, DBP, DIBP, we're still detecting the same phthalates that we're finding worldwide. So this is consistent with the literature. Now, the last part of my project that I haven't quite gotten to yet is actually calculating those inhalation rates of phthalates. And once the data comes back from the rest of the summer season, I'll be able to calculate the inhalation rate for the summer season using this fancy equation here, DI, which is daily intake, which is essentially the amount of phthalates that you'll inhale over the course of one day, assuming you're standing outside. And then sea air, which is the concentration of phthalates that I detect in my samples. So I'll take an average over the course of the season and use that. F is the exposure fraction, and IR is the inhalation rate. Now, for this particular study, I will be using the inhalation rate of students because I think that is the best representative of the population surrounding the air sampling trailers that I have, considering the fact that the air sampling trailers are on a university campus. I think it's only right. So I do have quite a long road ahead of me. I'm going to continue sampling all the way through April because I started this past summer and I want to determine any trends in seasonality. So starting in summer, ending in spring, which is April, and throughout the whole time I'll begin calculating the inhalation rates as the seasons pass and see if there's any trends in seasonality, because that is also a relationship that is not quite understood in outdoor phthalate detection across the world. So the main things I'd like you all to go home with is the fact that over this past summer, out of the 14 phthalates, the 6 that were detected averaged between 4.1 plus or minus 7.3 nanograms per cubic meter, which is a lot lower than the literature. But I'm still detecting the same identity of phthalates. There is also no correlation between total PM10 and phthalate concentration in the atmosphere, at least from what I've detected, and that diethylhexyl phthalate, DEHP, had the highest concentration, which is also similar to the literature. I would really like to give a big thank you to my advisor, Dr. Julie Leishak. She's been a wonderful help this whole time, as well as my roommate, Kira Halcomb, and all these wonderful other people. Pacific University and PRISM for funding, as well as the Oregon Department of Environmental Quality, DEQ. If you haven't heard of them, they monitor the air and they deal with air sampling instruments all the time, so they were a big help, as well as the Portland Area Air Quality Research Consortium. Without them, this research would not have been possible. Thank you.
Thank you, Nicole, for that wonderful talk. I am now here to redirect everybody inwards toward your tables, talk about the main things that you took away from that talk and any questions that you have. We're going to share questions in about 1 minute. Well done. Thanks. Very good job. Thank you. You're feeling the relief?
It
it's always like the third or fourth slide in, the nerves just go, and then you start like rolling into your talk, right? And then it was just like natural from there on. So it was just super nerve-wracking because I've never presented in front of this many people.
That's why you're here now?
But it's true what they say. Presenting to a bigger crowd is easier than like a small crowd of 20 people. Because then you feel like all 20 people staring at you.
Right.
And like here, like I couldn't focus on one person.
Right. And also you'll never see most of these people again.
Exactly. So yeah, it was good. Thank you for introducing me.
Of course. That's my job.
Appreciate it. It's so fun to be here.
I'm glad. I was here as an undergrad a long time ago.
Really?
Yeah, I presented a poster, not an oral presentation.
I presented a poster last year, so now this year I had to step it up.
Welcome back.
Thank you. It's so fun.
All right, I'm here to urge people with a question, possibly your table representative, to make your way to the microphone. And we have plenty of time for questions, so don't be shy. Even if there's a line, you can join it.
Hi.
Thank you so much.
Great presentation. I'm wondering, are phthalates naturally occurring, and have they been tracked like over time, or is this like very recent?
Good question. I am not entirely sure if they are or aren't naturally occurring. There's so many derivatives of phthalates that it's hard to like just say, because I feel like some are and some aren't. And I would say that this is very recent. That's why there is little to no data, at least in outdoor, because there are indoor sampling. But yes, it's becoming more prevalent these days as the data and the research is coming in. They are becoming more concerning.
Thank you.
You're welcome.
Oh, this is tall. Okay. Hi. So forest growth city planning involves a lot of trees. Do you think that the amount of like foliage affects phthalate concentrations in the air?
I don't quite know, but I'm gonna say my best guess would be not really, considering the fact that most phthalates are added to things like plastics and man-made products, but it's entirely possible that they are added to equipment used for like anything of that sort.
Yeah.
At
No,
least
it's
in
just-
like the instruments or machinery that they might use.
Yeah, we also are near an industrial area
Mhm.
at Pacific University, but I think we asked you this question over the summer, and we're not really sure if it does anything either.
It's hard to pinpoint that.
Yeah, thank you.
This kind of extends off of her question. I noticed one of your figures, you had like the state of Oregon, and like you had a star showing a sampling and an arrow. Just out of curiosity, are you planning on sampling like multiple sites in Oregon? Just because I saw that arrow, and if you are you sort of thinking about like, you know, in Oregon, obviously we don't have as much industrialization as like those other places, like you mentioned, like in China, but like, do you think, you know, in a more Pacific Northwest foresty region will have like different results than like maybe, you know, Eastern Oregon where there's like maybe 2 trees in like Eastern Oregon. So like, are you planning on sampling like in different places, and do you think there will be like differences based on like environment and stuff like that?
Yeah, that's a great question. So the 2 air sampling trailers that we have were actually really hard to get a hold of. And so I don't have any say in where the air sampling trailers are located, considering that they are gifted to us, or they're still in partnership with the Portland Area Air Quality Consortium. And so they're kind of still in ownership of those ones, so they decide the location. And so I can't really just pick wherever, but my guess would be that in a more like urban area with a place with 2 trees would probably have more or higher phthalate concentrations. It honestly depends on the industries located around it. For places like China, they are the world's leading plastic recycling. So that is a large place for phthalates to like enter the environment or re-enter the environment. And so as it really depends on the industry located near the sampling site, but yeah.
Thank you.
Hi, in one of your figures, it showed a large increase in phthalates in July, I think it was. And I was
Yes.
wondering if you had any initial explanations as to why that occurred.
Yeah, so good question. We were originally thinking that we would see a spike in phthalates after the 4th of July, but as you might have noticed, there was a sampling date on the 6th of July that was significantly lower. And so essentially, I have absolutely no idea what was going on July 12th. But there was a house being built right next to one of our sampling sites. So it's entirely possible they were doing something fancy that day that just went right into our air samplers, but I honestly couldn't tell you.
Okay, cool. Thank you.
That was sort of my question, so I'm thinking on my feet. Did that July 12th data point get added to your FIT? Was that the same massive outlier?
For the PM10 concentrations versus phthalate? Yes. So we did a Grubbs test, and it's still in.
It's still in?
It's
Okay.
there.
Okay, thank you.
It counts. Yeah.
I was wondering for the previous data that you have for concentrations in different cities like Mexico City and Beijing, if those are like averaged over a year or if they're taken during a specific season?
Yeah, so in the graphs that I had, I must have forgot to mention that those depict the average maximum concentrations of a single phthalate, likely DEHP. And so that's just the concentration of one phthalate, not the concentration of all. Yeah.
Thank you.
Mm-hmm.
So I was wondering, if we're worried about the risks of potentially inhaling phthalates, how worried should we also be about the direct contact that we might have with phthalates on a day-to-day basis? And or if you have any information on like how it might be metabolized differently between those two like contact methods?
Mm-hmm. Yeah, so, sorry. Unfortunately, my research solely exists to measure the phthalate concentrations in the atmosphere. The extent of my knowledge is that when inhaled or absorbed or digested, right, they can have the potential to cause adverse effects. Unfortunately, I don't know what concentrations are considered harmful. It is true that we are all exposed to phthalates at very low concentrations all the time. I honestly wouldn't concern yourself with it, but the whole point of my presentation here is the fact that if I am able to collect data to calculate what the exposure rate is, we can then use exposure to determine risk. And so mine is just kind of the preliminary data, like what are we exposed to? Using the exposure rates, we can determine risk. So my data will be handed off to someone else to answer a question like that.
Thank you.
Mm-hmm.
Hi, did you notice any differences in concentration when you were sampling in like low wind versus high wind settings?
We didn't really have a way of measuring wind, if I'm not mistaken. We only recorded weather such as like rain and such things, but for the most part in Forest Grove it wasn't really that windy, though wind does have a tendency to dilute the concentrations in the air, because if you have a really concentrated area here and a less concentrated area here, it just swipes it all through. So it would likely be that the higher wind, the lower the concentration.
Okay.
Thank you. Let's thank Nicole one more time.
Thank you so much.
And our next presenter is Hannah Halstead at 11 a.m. We'll see you here soon. This is the moment of peak nerves. It'll get easier once it gets started. Is this your first time at Murdock? Yeah. Oh, congratulations. Thank you. It's my first time like presenting. Yeah. You can do it. You're gonna be great. You've practiced this. When I was an undergrad, I also came to Murdock because I went to undergrad at Penn. Then I only presented a poster, and I was always very impressed by the people who are presenting oral presentations on their first time at Murdock. It's a lot. I see that you have water. That was very smart. If you run out or would prefer, you're welcome to take one of those as well. I think that I talked you through my spiel. I'll be sitting right here at this computer. And when you have 3 minutes left, I'm going to flag you this 3-minute sign. When you have 1 minute left, I'll flag you this 1 minute sign. Just just make sure to like sort of check in and pay attention to that corner every so often as you get into it. Otherwise these won't help because you won't see them. Also, we have a slide advancer if you would like to use it. If you press the forward button, that'll bring your slide forward. This little one off to the side. This one brings it back. No idea what that does. It's a mystery. This one is the laser. Okay, excellent. Where, I have on my list where you came from. Oh, you came from Western Washington. Yeah. In Pullman, right? Bellingham. I'm so sorry. Washington State is in Pullman, I think. WSU. Yeah. Did you drive down yesterday? Do you have a big group?
No, not really.
Sometimes
when I was driving down, I just went with like my advisor.
Yeah. How long is the drive from Bellingham? It's a bit. Yeah.
4 hours.
Yeah. And then you're staying. Everybody. I'm at Reed, so I'm just down the road. But I think everybody who's traveling is staying at the hotel, right?
Yeah, I mean my advisor's staying at
But like
me and some others.
Nice, good. Then you don't have to get up quite as early to make it here on time.
Yeah, still pretty early.
It is still very early, yes, but. The best thing about giving a talk in the morning of the first day is that you just get to enjoy the rest of the day.
I know. That's why I was really happy.
Yeah. This is a good time. People are waking up, they're loosening up. All right, if you are joining us back from the break, I invite you to sit at any table, meet new people if you're new to this room. It is my honor to introduce Hannah Halstead, who comes to us from Western Washington University in Bellingham, who's going to give us a presentation about nickel-palladium catalysts for selective hydrogenation reactions. Take it away, Hannah.
Hi, I'm a senior chemistry student at Western Washington University, and my research has to do with nickel-palladium phosphide catalysts for selective hydrogenation reactions. The United States has an overabundance of ethane and propane from natural gas production. Ethane's production in particular has just about doubled in the past decade, and ethane, which is a carbon-carbon single bond, is usually converted into ethylene, which is a carbon-carbon double bond, via catalytic steam cracking. But this process produces trace amounts of acetylene, a carbon-carbon triple bond, as an impurity. And acetylene impurities have to be removed from ethylene monomers used in the production of polymers, specifically, of course, polyethylene, which has many uses, all the way from like plastics to antifreeze. So the scope of our project is to develop a new class of catalysts for the selective hydrogenation of alkynes, which is the carbon-carbon triple bond, to alkenes, the carbon-carbon double bond, while minimizing the use of expensive noble metals. But before we continue, let's just remind ourselves what a catalyst is. So a catalyst increases the rate of chemical reaction without any permanent chemical change to the catalyst itself. And over here, you can see an energy reaction coordinate diagram. You can see our reactants over here have to overcome this energy barrier in order to become our products. And without the catalyst, it has a much bigger energy barrier than it does with the catalyst. So it gives an easier way for the reaction to take place. So if you were to ride a bike up one of these two hills, so to speak, you would have a much easier and faster time going up the red hill with the catalyst than you would the black one. And specifically, we make heterogeneous catalysts. And that means that they're in a different phase than our reactants and products. And like most heterogeneous catalysts, Our catalysts are in the solid state, while our reactants and products are in the liquid state. And here you can see a little figure. These like green and blue particles are our catalysts themselves, while this red and gray thing right here is the support which we put our catalyst onto. And to do that, we take nickel-2 nitrate, ammonium dihydrogen phosphate, and sometimes palladium nitrate, and we dissolve it in water and impregnate it dropwise onto our support, which is silica. Now, silica is an inert support, meaning it is non-reactive, and it is also mesoporous, meaning it has these little pores in them. So as we add our reagent solution, we do it until those pores fill up, which we call incipient wetness, and it kind of looks like wet sand over here. We then dry our catalyst precursor, so the water evaporates off, just leaving with us our reagents. And you can see a nickel catalyst here on silica and a nickel phosphide, so kind of different colors, but pretty similar. Then we calcine our catalyst, so we bring it up to 400 degrees Celsius in air in order to oxidize it. And here again, you can see our nickel catalyst, which is dark gray in color, while a nickel phosphide, this is specifically Ni12P5, is lighter and more brown in color. Then we reduce it or activate our catalyst. So we bring it up to 650 or 550 degrees Celsius, and we do it under a flow of hydrogen gas. And after the reduction, our catalyst particles themselves are a little bit smaller, meaning we have more surface area and more active sites for our reactants to bind to, which is a really good thing. And after the reduction, you'll notice they're both black in color. So how do we make sure that what we synthesized is what we are intending to create? And for that, we use X-ray diffraction. So here we have 15 weight% of our nickel and nickel phosphide catalysts, with down here being nickel, Ni3P, Ni12P5, and Ni2P all on silica. And you'll notice that each one of these have a unique diffraction pattern that we can use to distinguish from each other. We can also use transition electron microscopy. So here we have an image of 2.5 weight% Ni3P on silica. And this big particle here is just our silica. And these little dark areas are actually our catalysts that are anchored onto the support. If we were to zoom in on one of those, it might be a little tough to see for you in the back, but there's these regions where there's lines. And that's actually our catalysts themselves. It's the planes of the lattice that we're seeing, of the atoms, and which is how we know that our catalysts are 3 to 5 nanometers in size. We also do catalytic testing on 2.5 weight% of our catalyst, because that's much closer to the low weight% that is used in industry. And to get a better look of what these atomic planes actually look like, we can look at these surface structures. So you'll notice that for our nickel catalyst over here, that it's just basically a two-dimensional sheet of nickel atoms. And as we add in more phosphorus, something interesting happens as the atoms have to rearrange themselves to be in a lower energy state. The nickel is basically diluted from the surface of our catalyst, meaning that our reactants and products will bond differently to the surface, creating different catalytic properties for each of them. And of course, for our stoichiometric phosphorus to nickel ratio, nickel has the least. Our next highest is Ni3P with a ratio of 0.33, then Ni12P5 with a ratio of 0.42, and then finally Ni2P is our most phosphorus-rich force with a ratio of 0.5. And to actually test these catalysts, we use a trickle bed reactor, and here you can see the one that we actually use in the lab, as well as like a little schematic so it's easier to tell what's going on. So we make 1,000 parts per million of phenylacetylene, which is our triple bond over here, and we put it into 2-propanol as a solvent. We then pump it very slowly, about 0.9 milliliters per minute, under 10% hydrogen gas, through our catalyst. We collect it at the other end over here, over a range of 30 to 75 degrees Celsius. And to analyze the sample we get out of this, we use gas chromatography. And again, you can see what we actually use in the lab here. So we put our sample in, and out we get this chromatogram. And this huge peak you see here is 2-propanol, which is our solvent. And then here we have phenylacetylene. What I didn't mention is we also add 500 parts per million of heptane, which we use as a reference after it goes through. So here we have our reactor effluent, meaning it has gone through our catalyst. And you'll notice that the phenylacetylene peak has almost completely disappeared, meaning it has been either converted into styrene or ethylbenzene. So now we can take a look at how each of our different catalysts perform. Here we have the percent of phenylacetylene that we're able to convert to either styrene or ethylbenzene. as a function of temperature. And the first thing I'd like to point your attention to is as we increase in temperature, overall across all the catalysts, that we see an increase in the amount of phenylacetylene that we're able to convert. Next thing I'd like to draw your attention to is this blue line up here. That's our nickel catalyst on silica. And as we add more and more phosphorus, our conversion gets worse and worse, okay? And then if we're to take a look at styrene selectivity, which is how much of our phenylacetylene is being converted into styrene and not ethylbenzene. Now this is really important for our catalysts, because if going back to all the way back to ethylbenzene means we have to start the process all over again. Because I started this talk by saying that the single bond is being converted into the double bond, and it makes the triple bond as an impurity, which we're trying to get rid of. So if we go all the way back to the beginning, we have to start the process all over again, which is a waste of money and resources, really bad stuff. So if we take a look here, you'll notice that as we increase in temperature at this time, that the selectivity tends to decrease. And this blue line over here, our nickel catalyst, that had really good conversion, suddenly has the worst selectivity. And as it turns out, as we increase in our phosphorus, we get better and better selectivity. So Ni2P, our most phosphorus-rich force, that has the best conversion, or sorry, the worst conversion, has the best selectivity. We can see this more easily if we focus on a single temperature, 45 degrees Celsius. We can see if our conversion and selectivity as a function of phosphorus to nickel ratios, as we increase in phosphorus, that we go down in conversion, but we go up in selectivity. So then the real question is, how do we keep the selectivity that we need while getting all the conversion that we really want, right? So to do that, we tried substituting small amounts of palladium into the nickel phosphide lattice. And here you can see another X-ray diffraction image. Down here, we have pure Ni2P, meaning it has no palladium substituted in. And each one going up, we've substituted a little bit more palladium. And when I say I'm substituting palladium in, that means for our nickel phosphide lattice, for every so many nickels, I'm replacing one of them with a palladium atom. And I know that we're doing that because we're only seeing Ni2P peaks, no palladium aggregating out. And also, if we were to zoom in on the peak right around 40 here, you'll notice that as we increase in palladium, our peaks are actually shifting. And this is because of how X-ray diffraction itself works. So basically, the instrument fires an X-ray at your sample, it hits one of the atoms in the planes of the lattice, and of course, like the name suggests, it diffracts, and the instrument measures that angle of diffraction. And palladium has a bigger atomic radius than nickel does. So when you insert it into the lattice has to expand in order to accommodate it. And that expansion causes the angle to decrease, and is how we know that we're successfully substituting the palladium into our nickel phosphide lattice. So then to compare to see how this nickel phosphide palladium substitute catalyst behaves, we can see again our phenylacetylene conversion, with the red line being having some palladium substituted in. You'll notice across each and every temperature that we see better conversion. But of course, if we look at our selectivity, you'll notice that across each temperature that we do see a drop. But if we do look at our 45-degree temperature on each of these, you'll notice that we see a relatively small drop in selectivity in comparison to a pretty big gain in conversion. So we tried substituting the same amount of palladium into each of our different catalysts to see what would happen. So here we have our just normal nickel phosphides for conversion and selectivity. Then adding the same amount of palladium, you'll see over here our most nickel-rich phases, being of course pure nickel and Ni3P. We see relatively modest boosts in conversion. But if we look at our more phosphorus-rich phases, being Ni12P5 and Ni2P, we see much bigger gains in their conversion compared to what they originally were. And if we take a look at our selectivity, you'll notice that the phases that had only a little bit of a boost in conversion had the biggest drop-off in selectivity. And the phases that had the biggest boost in conversion only saw marginal damage to their selectivity. So then we decided to take another look at Ni2P because it has our best selectivity, what we like the most. And we tried varying the amount of palladium that we were substituting into it. So here we can see Ni2P and then the amount of palladium we substituted in before, and then even more, okay? So we're seeing even more of a conversion boost. And then, of course, like we would have expected, an even bigger drop in selectivity. So that's how we know like our trend is going, right? So the goal of the project was to develop a new class of catalysts for the selective hydrogenation of alkynes to alkenes, while minimizing the use of expensive noble metals, namely palladium. In terms of our phenylacetylene conversion, that is our triple bond, it decreases significantly as we increase the phosphorus to nickel ratio, but it increases as we add more palladium into the lattice, which is inverse to what we see with our selectivity, which increases as we add more phosphorus, but it decreases as we substitute more palladium in. And here we can see a palladium nanoparticle that is more used in industry. They use about 950 palladium atoms, while some of the ones that we're currently investigating would only use about 50. So that's a big reduction in those expensive noble metals. I'd like to acknowledge the Western Washington University Department of Chemistry, the Advanced Material Science and Engineering Center. We have our funding from the American Chemical Society Petroleum Research Fund, the National Science Foundation, and the Research Corporation for Science Advancement. I'd also like to acknowledge and thank the Dr. Bussell's research group that I'm a part of, all lovely, wonderful, brilliant people that I've loved to work with. I'd like to especially acknowledge and thank a member of our group, Evan Stern, as we've been working towards this project together, and this presentation is a culmination of both of our works. And of course, thank you for listening.
Thank you so much. I would invite you to chat with the people at your table and discuss your takeaways and questions. And when you have questions ready, you're welcome to line up at the microphone. How does it feel? It was very good. It was very clear. And your pacing was beautiful. Was it? Yeah. That's good.
I probably skipped over some things, but that's fine.
It sounds like a really interesting project. How are you feeling about questions?
I prepared a bunch of questions, I think, and I know the answers to those pretty well. So
It's also totally fine to say that you're not sure and just give your thoughts. That's never a problem. All right, we have plenty of time for questions, so I encourage more people to stand up in the line at the mic, and I'm going to turn it over to our first question.
Okay, cool. So I was curious, so you mentioned that you kind of developed the active sites and then you started adding palladium. Was there any other noble metals that you tried adding, or were those kind of like already eliminated in in other research as well?
we haven't tried adding in other noble metals as of right now. I mean, the reason that we chose palladium is because it's so good at dissociating hydrogens, which is what we need for the selective hydrogenation reaction.
Right. Okay.
Yeah.
Cool. Thank you.
So I'm pretty ignorant when it comes to chemistry, but is there a good reason why we see the inverse relationship between like the reactivity and the selectivity? Is that something you can model, or there's like why we know why it's like that, or is that just something we've noticed and seen?
So basically here, if I go back to this slide, so basically our nickel atoms is what's contributing to our conversion. And let's see, since this is a selective hydrogenation reaction, it means we want to go from triple bond to double bond without going all the way to single bond. But going from the double bond to single bond is like the same kind of reaction. So if you just have more active sites in general, to bond to, you're more likely to go all the way back to single. So what like our phosphorus is doing here in splitting up our nickel atoms is making it so it's less likely to happen. But that also means it's less likely for the phenylacetylene, our triple bond, to bond to the active sites in general. So it'll go down.
Hi. I'm just curious about the reusability of this catalyst, and have there been attempts to make it more green?
Yeah, so good question. I know it's used to like make plastics, right? We're also looking into how it can be used for plastic upcycling as well, but we're still kind of in the preliminary like research into that, so I don't really have much to say, but we are looking into it for sure.
Thank you.
Hi there. I noticed uncertainty bars are not shown in any of your graphs. Did you guys do any uncertainty calculations?
We do have uncertainty calculations. They're pretty similar between each of these, so we didn't really show them, but there is like a little bit of
Oh,
uncertainty.
are they just like really small?
Yeah, it's pretty small and it's pretty consistent, so.
Oh, that's good. Wait, one more thing.
Yeah.
There you go.
So this topic is very like narrowed and focused, and I was just curious, like what drew your group to studying this concept?
That's a really good question. I'm not really sure. I mean, we do also have like other projects that we're doing that has to do more with like greenhouse gases for catalysts for that, photocatalysts for that. So like this isn't the only thing that we're doing, it's just specifically what I'm doing. I don't know, I just think it's really interesting.
Cool, thank you.
Well done. Thank you so much, Hannah. Let's thank Hannah again. And then our last but not least presentation starts at 11:25. Catherine Woodburn. See you then.
We drove down right after our labs ended.
Yeah.
So,
Yeah.
yeah. It's a nice nighttime drive. But I'm excited to drive back in the daytime and see the gorge.
Exactly. Yeah. Where are you from?
Cupertino, California, so Bay Area. Yeah.
Have you driven through the gorge before? Did you fly directly
flying to Walla Walla, but I'm also on our swim team, so I've done the drive a few times.
Right.
Yeah.
It's always my favorite. It never gets old.
Yeah. Yeah. I'm excited. We'll drive back up tomorrow. But yeah.
It's always a whirlwind.
Yeah. For sure.
They have you in this hotel?
Yeah.
Nice.
Yep.
Just roll out of bed, get dressed, and then get breakfast. Good.
Yeah.
Yeah, because it's so early.
Yeah. Is Reed staying in this? Okay.
Because we're only a 30-minute or so drive away.
Oh, okay. Yeah.
So it's really not that bad, and it's nice to be able to go home at the end of the night. But it was tough getting here at 6:45.
I bet.
Yeah.
I'm sure.
But it is all worth it. I always love the energy of the room.
Yeah. It's wild to see so many people. But
What year are you in?
I'm a senior.
Senior. So have you finished all the major classes, or you have a couple left?
Yeah, we're currently in them. Professor McCauken's inorganic.
Yeah, yeah.
Tim is awesome.
Yeah. Yep,
and
I took quant and inorganic from Tim when I was a
Yeah.
student.
Yeah, he's hilarious. Definitely a rigorous class, but
One of my favorites. Yeah. When I took it from him before he'd gotten tenure.
Okay.
And so it might be a little bit different now, but one of the things that I always loved about it is that it was clear that he worked as much as we did in class.
Yeah.
We would be like working in the science building late at night at 11 and 12, and he would still be there too.
yeah. I don't think he's there quite as late, but there's been a few
That's
days
probably
where
good for
I'll
him.
run into Tim or something at 7 p.m.
Yeah.
He's going home.
Yeah, I really enjoyed quantitative analysis and equilibrium when I took it, and I asked, Tim was there at like 2 in the morning one day, like his door was mostly closed, but it was like you could see the light on in the background. And I knocked on the door, and you could just hear like the hello, like the I really don't want to, and I was like, can I take it for quant? And he was like, why are you asking right now? And I was like, you're here. Yeah. I thought about it. And then the next day, a bunch of my other friends asked TA, and so I was like, you see, it was important.
Yeah.
Yeah, it did not used to be as uncommon to see him there at really awful hours. So I'm glad that he's gotten a little bit more
he's gotten
balance.
a little bit more.
Yeah.
He has a cat now.
What?
Yeah.
Is that must be recent.
It's recent, this summer. Yeah. One of our psychology professors breeds Siamese cats. We got one of her little kittens. It has like blue legs and blue eyes. We named it Claudia with a W.
That's wild.
Yeah.
Does he talk about the hairless cats very often?
No.
He likes hairless cats.
Okay.
Or at least that was the impression that he gave us like 12 years ago.
I believe it.
So I'm surprised. I'm shocked that he got a cat, and I'm surprised that it has hair.
Yeah. Yes. Yeah. He was bummed though. He said he wanted to name it Positron, but his wife Amy wouldn't let him.
Yeah, Amy. I was a German chem double major, and Amy was Amy at the time was appointed in German.
Gotcha.
It was my German advisor.
Yeah.
All right. Welcome back, everybody. It is my honor to introduce Catherine Woodburn, who comes to us from Whitman College. She's going to present to us on understanding zinc sulfide syntheses and co-product evolution through a kinetics-based investigation of dual and single source precursors. Take it away, Catherine.
All right. Hi, everyone. I'm Catherine. I'm a senior chemistry major at Whitman College, and I'm going to walk us through what my group has been doing to investigate zinc sulfide. So first, a little crash course in nanocrystals. What are they? We think of a nanocrystal as having an inorganic crystalline core. So for my zinc sulfide nanocrystals, that's zinc and sulfur in a specific ratio, bonded in a specific atomic arrangement, and that nanocrystal is surrounded or coated on the surface with organic ligands. Those organic ligands are made to increase solubility. So we make these nanocrystals in nonpolar solvents. So our organic ligands could be something like oleic acid, where it's a longer carbon chain to help it stay in solution and not precipitate out. Nanocrystals are typically on the scale of 5 to 10 nanometers, but they can range to hundreds. But our crystals tend to fall in the 5 to 10 nanometer range. With zinc sulfide and other semiconductor nanocrystals, we can think of them as being quantum dots. So for a bulk zinc sulfide sample that you would find out in nature, we consider that electronic structure as having this valence band and then conduction band. You've got your valence electrons kind of hanging out in the valence band. If you were to absorb any energy, you would kick electrons up to the conduction band. Those are shown as shades because they don't really have discrete energy states. So you could be exciting from anywhere up into that bulk conduction band. For semiconducting quantum dot, essentially we've tuned that size small enough that we allow quantum mechanics to take over, and so we have discrete energy steps within that nanocrystal. So depending on the size of your crystal, you're essentially changing the size of your band gap. So for a larger crystal, you're going to have a smaller band gap that's smaller than the gap of a bulk crystal, and then as you make that crystal smaller in size, you're changing its electronic properties by tuning the size of the energy gap between exciting an electron. So with that introduction, I'll jump into how we consider our reaction syntheses. Or first, I'll talk about a little bit more how we can kind of learn about our nanocrystals. There's many different ways to think about nanocrystals. For our group specifically, we're looking at NMR, so nuclear magnetic resonance, and then UV-Vis spectroscopy, as ways to analyze whether or not we have our crystals, what size they are, how fast they're growing, and what other products do we have attached to the surfaces of those crystals or that are in solution with our crystals. Nuclear magnetic resonance is a technique commonly used in organic chemistry that is thinking about different atoms in a molecule will experience different chemical shifts depending on what other atoms they're around. We can tune an NMR to look at a specific kind of atom, so think a proton, for example, and whether or not that proton is attached to a carbon, attached to other protons, near a fluorine or an oxygen. It's experiencing a different electron density, and that's going to make it appear as a different signal in the NMR when exposed to that magnetic environment. For UV-Vis, that's essentially looking at what energies of light a molecule is absorbing. For our crystals, the crystals will absorb a certain size of light as that band gap. And as we grow our crystals, we're decreasing that band gap, and we'll see crystals kind of grow in according to that size of the band gap that they're absorbing. So with that, I will now launch into how we think about our crystal strategies. The first one is what we refer to as a dual or kind of traditional precursor synthesis. You have a metal carboxylate. For us, that's going to be zinc oleate. And then you have a chalcogen source. So for our lab, that's a substituted thiourea. We can tune the different R groups on there depending on what kind of functionality or properties we want that thiourea to have. When we combine our metal precursor and our sulfur precursor, we assume they undergo this kind of slow conversion step into a solute coproduct species. Some people refer to this as a monomer. I'll refer to it as a solute. To our knowledge, this hasn't been able to be isolated in solution. It's too short-lived. But then once we have that, we assume it undergoes a relatively quick conversion into nucleation and growth of those nanocrystals. When we're looking at how our precursors are first converting into that solute species, we think of the metal and the sulfur kind of closely combining in a structure that looks similar to this. It's important to note that there's been really good control over the sulfur precursor. By tuning those different R groups, we can really tune the reactivity of how it's interacting with the metal, but there's been traditionally difficult control over the metal precursor. So another strategy used to do that is to essentially ask the sulfur or the chalcogen source to be a good influence on our metal by combining them in the same molecule before we begin the reaction. And that's our single source precursor synthesis. So as you can see, it has a similar structure to what we imagine this kind of intermediate transition state to be, where that metal and that sulfur are already closely interacting in the same molecule. Again, that still needs energy, and it's going to undergo a relatively slow conversion step into the solute coproduct species, and then a quick conversion into that nanocrystal. Because the metal and sulfur are already closely associated, we would kind of suspect that our single source precursors need different amounts of energy compared to two separate precursors to react. To walk us through how our group is producing these thioureas, you can make thousands of these thioureas depending on what substituents you first use. So here we take a substituted isothiocyanate. Here it's a hexyl isothiocyanate. We combine that with an amine, so we're thinking dioctylamine. Both of these reagents are commercially available, they're relatively cheap, and you can really see the wide variety we could use. You can have aromatic systems, straight-chained, saturated, unsaturated. You can functionalize your aromatics. Essentially, if we combine those, we'll get a substitute thiourea, so a hexyl isothiocyanate with a dioctylamine will make a hexyl dioctyl thiourea. We confirm that we produce these thioureas using NMR. So like I mentioned earlier, that's acting on different chemical shifts. So the protons on the methyl groups at the end of those long carbon chains, for example, are going to show up at this kind of low parts per million shift, whereas this acidic proton on that nitrogen, which turns out to be really important later on, is showing up at a far different shift. So this is really helpful for us to confirm, okay, we've made the structure that we think we have, and we can bring it further through our reactions. Once we have that thiourea, so again, I'm kind of continuing that hexyl dioctyl precursor, we combine that with a zinc oleate and hexadecane and tetraglime, a nonpolar solution, to make our zinc sulfide. And the reason why I point out that acidic proton is we can use that as kind of an NMR handle to track the kinetics of our reactions. How fast are our reactions occurring by looking at the disappearance of that acidic proton peak. And then we can correlate that with a UV-Vis graph as well. So we're lucky and fortunate that some of our precursors absorb in the UV region where our crystals absorb. So you can see here that our thiourea peak is decreasing as we start to see that crystal growing in. You might be asking yourself, okay, you can track the kinetics with NMR, you can track the kinetics with UV-Vis, but do they match up? Is this a reliable way to measure them? And we think that they do. So they've got a similar kinetics kind of trace over time. We can use this similar reaction and similar way to monitor it with multiple different thioureas and multiple different substitution patterns on that thiourea. So for just a couple of examples, instead of a hexyl dioctyl thiourea, we have a trifluoromethylphenyl dioctyl thiourea. And again, you see a different kind of UV-Vis trace as that hexyl dioctyl, but we're still able to track it. And with this di-substituted, so a phenyl dodecyl thiourea, we similarly have a different kind of trace. This suggests that we would have different reactivity profiles between the different kinds of substitution on that thiourea, which again is support for using that as a way to tune the kinetics of our reactions, which in turn would change the size of our crystals, the properties of those crystals. And if we can tune our precursors, we can really select for a certain kind of nanocrystal we want. I'm going to walk us through a single source precursor really quick. So this is kind of transitioning from the traditional dual precursor. You have two separate precursors. First, we're combining those into the same molecule. Professor Dalia Biswas at Whitman College made this computational chemistry model for us of what we assume our single source precursor to look like. We use this to confirm that that zinc and the sulfur are seeming to associate in the single source precursor. We have some other data to suggest that this might not be acting as a monomer precursor in solution. It might be polymerizing. For time today, I won't be talking about that, but that's an important thing to note as we continue to understand the reactivity of these precursors. But essentially, you combine a thiourea with oleic acid and diethyl zinc. This is done in an air-free environment, and you produce your single source precursor. We can take these single source precursors through the same hot injection technique we used for the thioureas, but instead of needing those two precursors, we just have our one, so we heat that up in hexadecane and pentane and produce our zinc sulfide species. This is all backed up with our NMR aliquot approach, but shown here is the UV-Vis, and you can see that as that single source precursor peak is decreasing, we see the growth of a zinc sulfide nanocrystal. It seems to be on a different time scale, which makes sense given our hypothesis that these would have different reactivities. So compared to the precursors from the last slide, the thioureas, where we're seeing about 30 to 60 minutes, it seems here that we're getting reactivity or starting to get crystal growth at even the 20-minute scale. So again, that might be needing less heat, less energy to overcome that activation barrier in that first slow kinetic step. I'm not going to launch into a couple of our experiments using microwave or UV irradiation on these single source precursors. So for a microwave irradiation, we're using a microwave at a very specific wattage, not temperature, to provide the energy to produce our solute and then our nanocrystal species. Microwaves act on dipoles to heat up solutions. Our nonpolar hexadecane is not going to absorb many of those microwaves, so we're expecting that our solvent can be essentially transparent to the microwaves, and it's really our precursors that are absorbing that energy. We hypothesized this would be a different mechanism to the hot injection since it is microwave, but it's really exciting to note that we're getting crystals. So this is our hexyl dioctyl oleal single source precursor, and you can see somewhere between 30 to 40 minutes we're getting our crystals. With a different precursor, now we have a phenyl group on there, we again see different reactivity, but we are getting crystals. So that's really exciting. A kind of another route that I'm looking forward to investigating this year. With UV irradiation, this provides a way to have no heat necessary. We're using our precursors at room temperature and exposing them to UV light. We are getting crystals from our hexyldioctyl oleal single source precursor. Again, that's really exciting. That could reduce the potential kind of energy cost efficiency of these reactions. And we back that up with XRD, X-ray diffraction, to confirm that we were getting zinc sulfide, and you see we're getting sphalerite, which is a specific phase of zinc sulfide nanocrystals. With that, it's really exciting. We've had successful zinc sulfide syntheses from microwave irradiation, hot injection techniques, and UV irradiation, and we see reactivity profiles are different across the varying methods of initiating our reactions and the different precursors. So we're looking forward to investigating and teasing out those mechanismal differences. Our lab is fundamentally interested in the kinetics and mechanisms of our initial precursor conversions. And so we have a lot of promising data here to compare and contrast different mechanisms. With that, I'd like to thank Professor Mark Hendricks for all of his guidance, my current lab members, lab alumni, Professor Dahlia Biswas, Whitman College, and the MJ Murdock Charitable Trust for funding. Thank you.
Thank you for that wonderful talk. I'm going to again ask you to please chat with the people at your table and think of what questions you have. So 1 minute for chatting. I'm going to grab my list so I know what our time is. Excellent. And you're perfect on time.
Oh, thank you.
So we'll have lots of time for questions.
Great.
How are you feeling about questions?
It'll be interesting. It'll be good.
Yeah, it'll be good.
It'll be interesting.
It's totally fine. I think especially with, materials work, a lot of students haven't seen anything like it. So
Yeah.
but that means that you get a combination of like really fundamental questions that you can totally answer, and also questions that they don't realize how challenging the question
Exactly,
is.
yeah.
So it's totally fine to say, that's a bit beyond the scope, I'm not sure, this is maybe what I think. Don't worry about that.
Yeah.
We have plenty of time for questions, so if you or somebody at your table has a question, I encourage you to join the line behind the microphone.
Bob, my question is, as I was wondering if your reaction of the zinc sulfide nanocrystals is, if it's pH controlled, and if so, at what pH? Because you talk a lot about tracking the acidic protons. I was curious if you do that.
Yeah, that's a great question. Sorry, got surprised. Yeah, that's a great question. We aren't tracking pH. We're running these in nonpolar solvents. We're really using that acidic proton as a kind of NMR handle just to track its disappearance in terms of its presence on that NMR. We're assuming that as our thiourea precursor undergoes its conversion into zinc sulfide, and then whatever co-products are being made, that acidic proton might be exchanged, it might be lost, it's going to be exposed to other environments. So that's really how we're using that. We haven't kind of tested the pH of our solution.
Okay, I just bring it up because our work is kind of similar. I'd love to maybe chat with you later,
Yeah.
but pH is a big dependent on how fast our reactions go, and so it might be interesting tracking it, especially because you are using that acidic proton.
Yeah, that'd be great.
Thank you.
Thank you.
You talked a bit about the ligands on your zinc sulfide nanocrystals, but you talked a little bit more about how you're tuning your thiourea to specifically meet the needs of specific reactions you're doing. Are the ligands on your zinc sulfide nanocrystals just coming from those thioureas?
Yeah, that's another great question. So our ligands can come from those precursors. Certainly, everything we have in solution is our solvent, so hexadecane, tetraglyme, and then whatever is attached to our precursors. So we're assuming that as our precursors decompose, some of those ligands that are produced either by coproduct side reactions or that initial decomposition of the precursors are attaching to the surfaces of our nanocrystals. In turn, those might also be directing the growth of our crystals. That's an active area that we're kind of looking into. Yeah, hopefully that helps.
Yeah, thank you.
I know you mentioned near the end you're still looking into the mechanics of how all this works, but I was wondering if you have any idea on why, when you were doing it with the microwaves, it was such a sudden jump after 30 minutes, while all the other ones seemed very, like, relatively spread out over time.
Yeah. So with the microwave, or I guess I should say with the hot injection reactions, we're able to pull those aliquots directly out of our reaction vessel, so we're not disrupting kind of the conditions at all. With the microwave, it's a little different to get the aliquots, and depending on the length of time I expose my solution to in the microwave, it is eventually heating to a different temperature. So it's entirely possible that between the 30 to 40 minutes, I was reaching some kind of temperature that was providing enough heat, potentially more than just the microwaves, to those precursors in solution to get them to start to react. So we're going to do a few more kind of pointed experiments there to tease out exactly what's happening.
All right, thank you.
Yeah.
Hello. Thank you for your presentation very much. And I was wondering, for the ligated thioureas, is it possible to use smaller molecules and get the same sort of quality crystals as a result?
Smaller molecules than the thioureas?
Mm-hmm.
Yeah, so there's a bunch of different precursors used for zinc sulfide syntheses, other semiconducting nanomaterials. Our lab specifically is focusing on using the thioureas as our kind of precursor of choice, but there's definitely others. There's phosphines or phosphides, lots of other small molecules that you could use. We are interested more in the mechanism than kind of the phase of our crystal that we get out at the end, at least for zinc sulfide. So we're not necessarily as focused on kind of nanocrystal quality control, but we're hoping that whatever we learn from the mechanics or the mechanisms of how our precursors are evolving and our crystals are growing, we can use that to better select for certain crystals or certain reaction conditions.
All right, thank you very much.
Yeah.
Hello. Okay, so this is the low-hanging fruit of questions, but I've never heard of like zinc sulfide nanocrystals before, and I was just wondering, like, what are the purposes of synthesizing them, and like what uses do they have?
Yeah, zinc sulfide's a pretty useful nanomaterial. Zinc sulfide is really helpful as a wide band gap nanomaterial. So like I talked about before, that energy difference is really big for zinc sulfide. So it's used commonly as a shelling nanomaterial to be around other nanocrystals, and it can kind of act as an ozone layer in a sense, where it can help to trap energy or redirect energy back into the kind of core nanocrystal as a improved efficiency. It's also used in biological tagging, so there's a lot of kind of research into the functions of it there.
Cool, thank you so much.
Thank you.
Let's thank Catherine one last time. And that concludes the morning session. And so I thank you all for being a wonderful audience and asking so many questions. And I wish you a happy lunch.
Thank you.
Well done.
Thank you.
You did a great job with the questions.
Thank you.
And you did a great job rolling with the surprise.
Thank you.
On the side.
Surprise, I turned and saw my face.
Yeah, it would be a little bit unnerving to me. You handled it well.